Okay, so I think we're all good to get going. Thank you, everybody, for just kind of sticking with me over the mask requirement. I really appreciate it. A couple of things to mention just before we get started from today. So I recommend you get a textbook for the class. There are different formats you can get. You could get a hardcover, a soft cover, or an e-text. It's all your own preference. It doesn't matter which you get. Since we're not using the Mastering Physics assignments as any part of the evaluation, it is acceptable to buy a second-hand book if you have a friend who's selling one or whatever. If you buy the e-text, I've noticed students are running into a lot of trouble, and that trouble seems to be coming from the publisher's end. I can try to help, but for the most part, students are having to get in contact with the publisher.
Is there like a course ID?
There is a course ID, and I can give it to you. I don't remember it right now, but I will say that it won't help.
Okay, because I can I have it there. I can get to it. It
Yeah.
just says I need to get a course.
And it asks for the course ID, and when I give you the number, and I sure can,
Yeah.
what it's gonna say is that instructor is not accepting registrations.
Oh, okay.
So that's probably what you're gonna see. Then you gotta get on the Pearson support. If you go to the chat feature, they're pretty quick.
Yeah.
And within about a half an hour or so, they should give you a new code, which will work.
Okay.
But yes, I'm happy to provide that course ID, but it won't help. But if you want to try it, maybe you're the one who'll prove me wrong. I'm also having the trouble in my other course, so it really seems to be from Pearson's end. I recognize that this is frustrating for all of you, and I wish I was able to fix it on my end. So that's the book issue. The second is the first assignment for the class is currently open. To find those assignments, they're on Brightspace. You click Assessments and then Quiz. Just open up the quiz, work on it for a little while. When you've done as much as you feel like doing for the moment, you just hit Submit Quiz, close it all off, and you're done. When you're ready to work on it a little bit more, you just open up the quiz and try a new attempt. I gave it some thought, and ultimately I decided I don't care how many attempts you make. If you try it over and over and over until you get 100%, I'll actually be quite pleased. So to that end, everybody has unlimited attempts at the quiz, and it will tell you your mark as you go. So you can just keep trying until you get them all right. So feel free to use up as many attempts as you wish. I think those are the only housekeeping details. Any questions about anything before we jump in? So last day we did a review of simple harmonic motion. We defined period and frequency, angular frequency, amplitude. We came up with the equations of motion for simple harmonic motion. One thing I just realized I didn't point out at the very end of our last class, and maybe some of you have thought about this already, maybe not. You see how our position depends on cosine as a function of time? Position changes with respect to time, it bounces back and forth. Our acceleration, likewise, goes as a cosine and depends on time. Acceleration changes over time, it's sinusoidal. Because acceleration is not constant, you're not allowed to use kinematics. Okay, I realize coming from 1050 or 1020, you're used to using kinematics, and it's kind of a first thought without really thinking. If you try that here, it's not going to work.
Are we going to be using a phase constant source?
Yes, that's what we're starting with today. Okay, so I will just put my note right here, no kinematics. And that's because acceleration is not constant. Okay, at the beginning of every class, I'll typically put a question up. This question is a review from last time. So it's to see, are you on top of things? While you're sitting here for 5 minutes waiting for class to get started, I think it's probably a little bit more valuable to try this problem versus checking in on Facebook or whatever. So as the instructor side, I see the value. You guys probably see a value in shutting down for a few minutes. But anyway, these questions are here just to kind of see, did I understand everything last time? I'll always post the answers for this, but for the most part, I won't go through them in class. So that's going to be extra practice for you as well. Okay. And then I mentioned last time I was doing a homemade lecture capture. That's what this iPad is for here. It's recording the screen. I did film it last time and I posted it. I wasn't super happy with the audio, but you can hear it, so it's not bad. If you have to miss a class, I will try and stay on top of posting those videos. Okay, and now we're gonna come to what you just asked about the phase constant. So last day, we talked about simple harmonic motion, and we put up our graphs, and our graphs looked like this. So here was our set of graphs. You notice that the x-graph started at the amplitude. That made it a cosine graph, okay? And that's something you're probably real familiar with from high school. So my question to you would be, what if my graph didn't start at the amplitude? What if it started elsewhere? Can it still be called a sine or a cosine? Is it still sinusoidal? Is it fundamentally the same graph or fundamentally a different graph? My answer to that question is, this is still the same graph. It hasn't really changed. When you look at that graph, it still alternates, it still goes up and down, it still has that cosine feature. The only difference is, it has a different starting point. It shifted over a little bit, and we can account for that shift. So it's got the same amplitude, it's got the same period, same frequency, it just doesn't have the same starting point. So that's where what's called a phase constant comes in. So if we look at our beginning point right here, our initial point, x, at t equals 0, is not equal to the amplitude, and in fact, it is less than the amplitude. We've still got our same period, t. We can still write that in different places if we wish. So what we need to do is write down our equation to account for that different starting point, for the fact that it doesn't start at the amplitude. So now our equation of motion is still going to be x as a function of time, same amplitude, same cosine, same period and frequency and omega, times t plus. We need something else in here for this argument, and that something is called the phase constant. This term is probably familiar if you're coming from 1050. It's probably new if you're coming from 1020, 1021. So this phase constant, it is an angle, and it will very typically, almost always, be given in radians, not in degrees. Wouldn't be wrong to give it in degrees, but it's not how we do it. And what the phase constant does, it allows us to shift that starting point. So let's just test it. So if we take this equation and we put in t equals 0, that gives us x at t equals 0 is a times cosine of omega times 0 plus phi. So that leaves us a times cosine phi. Cosine of an angle is going to be a number that is less than 1. So you see our result is that the initial position is less than the amplitude. So yeah, this phase constant does what we ask it to do. It allows us to shift that starting point. What else? We can follow through the process that we did last time. If we take the derivative of position, we'll get the velocity equation. So velocity as a function of time is minus a omega sine omega t plus phi. Our acceleration is the derivative of velocity minus a omega squared cosine omega t plus phi. In a typical sort of problem, you would be given the initial position, probably given the initial velocity, or the sign of the initial velocity, and you'd be asked to find the phase constant and the amplitude. Okay, so that would be a typical kind of problem you might have seen in Physics 1050. Any questions? So if you've had a look at the notes that I posted before class, you probably see that there was a homework question. That homework question is intended to be a review for you. I'll just put it up for a moment. Over there. So here's some of the things you should be coming into this course able to do. You should be able to do some vector analysis. So these are vector things you should be able to take care of at this point. And here's a summary question, like a review question, all about simple harmonic motion. So if you're trying to make sure you're up to speed on simple harmonic motion, this is the sort of thing you should be able to answer. I'll write up and post kind of a long, detailed answer to go with this, so you can try it and have a look at it, make sure you're on top. Get in touch with me if you have any questions. Okay, now that clues up our review of chapter 14. Again, if you're looking for more practice about simple harmonic motion, maybe particularly if you've made the jump from Physics 1020 to this course, I've got a really long overview posted on Brightspace, a video with a bunch of examples. So if you're really looking to catch up, just because it's totally familiar, you can try that out. We're going to go ahead and get started on chapter 15, which is all about traveling waves. Primarily, we're going to look at traveling waves with a source in simple harmonic motion, but it is applicable to any traveling waves, but that's where we're going to focus. This is a picture of some ocean waves, so they're kind of fun waves to look at. Kind of, maybe everybody's seen ocean waves before, or pictures of them, or listened to them for some soothing music. So we're going to look at different ways to characterize a wave. So we'll look at how fast a wave moves, the wave speed. How high the waves are, that would be the amplitude. How far apart are the crests, that'll be a new thing called the wavelength. And how much energy is transferred as a wave moves. So those are going to be some of the things we're going to look at. I recommend you read through the first section of chapter 15. So that's got a lot of terminology and an overview. I'm only going to hit the highlights a little bit here. So here's one of my favorite things to argue about. And I'm going to let you guys argue your own position. So here's a wave taken at the Rogers Center a few years ago. Sadly, not by me. Maybe you can see it coming across the crowd. Okay, so that's the wave. Your book makes an argument that the wave that you see in a sporting stadium is a true wave. I take the counterpoint. I don't agree with your textbook. I don't think it's truly a wave. So I'm going to challenge all of you to keep an open mind as we discuss the definitions of a wave. You choose for yourself, do you think it's a wave or not? For what it's worth, if you Google this, is the wave a wave, you'll find it a split. Some people say it is, some people say it isn't. It got one heated, very heated one evening at the dinner table in our home. So we were split down the middle. Half of us said yes and half of us said no. So it's not a set answer, but it is a good discussion and a good thought process, right? It kind of lets you evaluate what you think. Let's go back to our slides. So our first definition will be of a wave itself. A traveling wave is an organized disturbance traveling through a medium with a well-defined speed. Okay, so some things to notice here. It says that a traveling wave is an organized disturbance. So what do we mean by a disturbance? Because that feels a little bit vague. A disturbance is not something you can pick up. If you throw a rock in the water, the rock is going to make ripples in the water. Those ripples would be the disturbance. So the ripples are the wave. Maybe still a little bit vague, but I think we're getting closer. So here's water. We've thrown a rock in. Here are some ripples in the water, spreading out from where we threw the rock in. That was the source of the wave. So the disturbance is these ripples. The next word, which might be new, is medium. What do we mean by a medium? Some of our waves require what's called a medium, and a medium is just a substance that a wave moves through. So for example, water waves or sound waves move through air. Air would be the medium. So the medium is the substance through or along which the wave moves. Um, so next, this is a good question. In our water wave here, we throw the rock in. The water will bob up and down a little bit. So here's a little bit of water. It's going to splash up, then it's going to fall back down. So the water itself, it moves up and down a little bit before it settles down, but it doesn't go anywhere. So the water goes up, comes back down, then it stays put. The water doesn't go from here to here. So if the water doesn't move, what exactly does move in a wave? What's transferred in a wave? There's a question. Pardon?
Energy?
Energy is exactly the right answer. So if you've been to the beach and you're standing at the edge of the water and some big waves come in, you can get knocked right off your feet. It can happen all the time, right? Another example is if you're playing music over your speakers or if you're at a concert and the music is really loud, it physically hurts your eardrums because all that energy hits your eardrums and makes it vibrate. So energy is the thing that's transferred. So that's our traveling wave. For our two kinds of traveling waves, we have two kinds of traveling waves. They're called mechanical and electromagnetic. In a mechanical wave, the waves propagate through and disturb a medium. So that would be like a water wave or a sound wave. We require some sort of source to get the wave going. So that source might be throwing a rock in the water. It could be turning on the music in our speaker for the sound wave. Yeah.
Didn't we also recently figure out you can have gravitational waves?
Yeah, there can be gravitational waves as well. They fall under EM waves. So that's one thing for our mechanical waves. It's got to have a source. Something has to start the wave. The next is that the wave has to propagate through the medium. For it to propagate, there has to be a means of propagation, right? So a wave on a string, little bits of the string push each other. Wave in the water, little bits of the water molecules push each other, and we have surface tension interacting. So we've got to get some interaction there to make the wave propagate. Our electromagnetic waves, and this is like the gravity waves that was in the news a few years back, or light waves, or radio waves, UV waves, gamma rays. All of those are electromagnetic. These are super interesting. They don't require any sort of medium. They can travel through a vacuum. Okay, that's kind of a weird idea. Kind of what pushes what in an electromagnetic wave because something's moving. Turns out an EM wave is an oscillation of coupled electric and magnetic fields, and those oscillate because they influence and affect each other, and they propagate, they self-propagate because they move and change. That's the end of this course and into Physics 2055. So we're not going to talk about that today, certainly, but we should get there by the end of the semester. So we'll talk about mechanical waves for a little bit. And there are three kinds of mechanical waves, transverse waves, longitudinal waves, and combination waves. I meant to bring a slinky, and I completely forgot because I wanted to show the waves. Do people mind if we take like a 40-second break for me to run it and grab a slinky? Is that okay? All right, I will be right back. slinky. If anybody be able to help me with the demonstration, all you have to do is hold one in. Yes? So you just hold that in still, and I'll come down here. You maybe just come towards me a little bit. Everybody more or less see? So the first wave we'll do is the transverse wave. To make a transverse wave, I'm just gonna flick my end up a little bit. So you can see that the bump goes down and then comes back. So with the transverse wave, I'm the source, I make it move. The bump travels down because the little bits of spring interact with each other. So that's the transverse. For the longitudinal, I'm gonna pinch a few of these coils together and then I'm gonna let it go. This one happens really fast. Okay, so there's still a disturbance, you can still see it, but it's not what most people picture when they think of a wave. So we'll do that one once more. So this time, we've still got the wave moving back and forth between us, but this time the coils move differently. Last time they went up and down, this time they go back and forth. So there's our two kinds of waves, transverse and longitudinal. Thank you for helping. So let's get some notes there about those two. So for our transverse wave, that's the one we'll talk about first. We make the wave, we have a source, that was my hand pulling it upwards. So the hand is the source. It makes a disturbance, which is the bump, and the disturbance travels down the slinky or down the rope. So this is the disturbance. And the disturbance is the wave. In my slinky, it traveled because the coils were pushing and pulling on each other. In a rope, it would be the tension in the rope. What else? When it travels, it has a speed, and that speed is called the wave speed. And the wave speed has a symbol of a lowercase v. With our transverse waves, that disturbance is moving up and down, but the wave is going down the string. So there's the defining feature of our transverse waves. The elements of the medium, the little bits of the string, they move perpendicular to the disturbance, to the wave. So transverse waves have a perpendicular motion on the medium. And it's disturbed from the equilibrium position. So the disturbance is the bump, the equilibrium would be the flat string. The string does move up and down, and the wave goes down along the length. We're going to come back around to doing the equations to figure out the speed with which this is going up and down. That speed is important, but the speed that this goes up and down is not the same as the speed that the disturbance travels down the line. So we kind of have two speeds happening in these waves. So we're going to come back to that speed in a bit. For our longitudinal waves, that was where I pinched the bit of the slinky and I let that compression travel down the line. So our longitudinal waves, they also have a disturbance. And that disturbance was the bit of the coils that were pressed close together. They traveled down the length of the slinky. It also has wave speed v. That comes back and forth. The coils, the wave moves, the wave travels because those coils are vibrating back and forth. So for our longitudinal waves, the motion of the coils, the element of the medium, is the same direction that the wave is moving. So it's parallel with our longitudinal waves. This turns out to be the same kind of waves as sound waves. Those are also longitudinal. And we do sound in the next chapter. Okay, questions here? So I said there were 3 kinds of waves. We did transverse, we did longitudinal. We also have, even though we won't talk about it very much in this class, we also have what's called combination waves. Sometimes it's not strictly transverse, not strictly longitudinal. Sometimes it's both at the same time, and those can be really interesting. So if we had a tank of water and we gave one end a shove, so this shove is our source. That shove would put energy into the system. That energy creates a disturbance which travels. So it makes a water wave or a disturbance. What's really interesting is that the bits of the disturbance, it moves a little back and forth and it moves a little up and down. It actually has kind of a circular motion. So that's really interesting in water waves. So it's both transverse and longitudinal. If you like this idea, if you think this is kind of interesting, you might enjoy an oceanography class because they would talk more about this in an oceanography class. So next, let's have a look at a wave on a string because this is where we'll settle in for a little while. If you want to investigate this yourself, there is a pretty neat simulation online. Google PhET wave on a string and you will get to it. So I already did a little video of it. So what we have here in this simulation is we have a piston that's moving up and down with simple harmonic motion. And it's moving with simple harmonic motion because I told it to, right? It doesn't inherently have to, but I choose to put it on a motor that makes it move that way. So it's moving up and down with simple harmonic motion. It makes the bits of string go up and down with simple harmonic motion, and then we end up getting a wave traveling down the string. Some things to notice are we have high points, those are called crests. We have some low points, those are called troughs. The height of the string at any given time would be measured to the equilibrium, that's the center position. That height depends on 2 things. It depends on where we are along the string and what time it is, so it changes with respect to position and time. Because this source is moving with simple harmonic motion, we call this a sinusoidal wave, so that'll be one of the terms we use. And we study these sinusoidal waves mostly because it's good to understand, because most of the information we take in the world comes from sound and light, and those are both sinusoidal waves with simple harmonic sources. So this is one of the reasons to study this. It also turns out that any kind of wave we could think of, with whatever shape, could just be considered a sum of sinusoidal waves, so that's another way, it's just for the analysis of the waves. So there's a look at the wave as it's moving. Let's add some of those things as notes. So we said we have a source and it's moving with simple harmonic motion. So this is our source. Since it's moving with simple harmonic motion, it has an amplitude A and a frequency F, also a period and an angular frequency. Because our source moves with simple harmonic motion, our wave overall is called a sinusoidal wave. Then we've got our high points, which are crests. And our low points, which are troughs. The biggest distance we can ever be from equilibrium, that's our amplitude. And the last thing we said was that the height of the string Y depends on position and time. So generally we're going to write Y as a function of X and T. So it depends on position and time. So what we're going to do for the next little bit is develop that equation for Y as a function of X and T. Okay, still good? Alright. So to start getting to that equation, what we're gonna do is let's start, we know it depends on position, we know it depends on time. Let's see if we can figure out the time dependence. Let's figure out the position dependence, then let's put them together to get the full picture, to get the full equation. So for our time dependence, we're going to ask what happens to any one piece of the string or any one element of the string as a function of time. So here on the picture, I've got that simulation, but I isolated it so we only look at one of the green dots. So we see that that green dot, that's one element of the string, that's one specific x. It moves up and down with simple harmonic motion. It's got amplitude A, it's got frequency F, period T. So that's what's happening to one bit of the string. So let's see if we can write an equation for that. So what happens to one piece of the string? Moves with simple harmonic motion over time. So it moves up and down, back and forth between positive amplitude. So at one point the wave on the string might look like this. And then over time it changes a little bit. So some amount of time later it could be down at the negative amplitude. So that's our wave moving over time. We know for a wave that's moving with simple harmonic motion over time that the height of the wave as a function of time is going to have a maximum value of A. It's moving with simple harmonic motion, so we get a cosine. The cosine comes from the simple harmonic motion. It repeats over time, so it has an angular frequency omega. Omega is 2 pi times the frequency, which is 2 pi over the period. Then we come to one of those pitfalls I warned you about. I said we got to be careful when we say omega is root k over m. Omega is not root k over m because there's no spring. So whenever we write down omega, we should think critically, kind of what system are we talking about? What are the physical parameters of our system? So whatever omega is here, it's not root k over m because there's no spring to have a spring constant. So we'll just be careful there. So we've got A times cosine of omega times t. We're talking about the time dependence. It may or may not start at the amplitude, so we'll include a phase constant. So this is the description of any one piece of the string as it moves as a function of time. This gives us our time variation of the string of any single piece. So there's one bit of the problem solved. Next we want to look at the position variation. Okay, so we've got the time dependence done. Next we care about the position dependence. Just trying to make sure people get through the notes before I kind of take it away. When you're up front, it feels like forever. When you're trying to scribble it down, it feels like no time at all. And I do post all of these afterwards, so if you miss a word or two, it's no problem. Okay. So to ask about the position variation, let's ask what happens at any one instant in time. So for any one instant in time, that really just means that we hit pause on our simulation. So I've got my wave moving. What I'm going to do is just hit pause. Okay, so when we hit pause, we're taking a snapshot. This is what's happening along the entire string at one point in time. So when we hit pause, we say we're taking a snapshot of the graph. When we look at this wave over time, something that jumps out at us is we still have that crest to crest. So here's a crest, Here's a crest. We still have repetition over space, just like we had repetition over time. But this crest to crest distance, it's not measured in seconds anymore. This one's not repeating in time, this one's repeating in space. So instead of a characteristic time, we have a characteristic distance, because we're looking at a spatial variation. This characteristic distance we call lambda. So lambda is what's called the wavelength. It's the distance between any two consecutive crests or any two consecutive troughs. And it's the distance for one complete cycle. Since it's a distance, we would typically measure it in meters, occasionally centimeters. So for our time variation, we had a characteristic time to period. For our position variation, we have a characteristic length, the wavelength. We still have the same behavior. This wave goes up and down between the positive amplitude and the negative amplitude. It repeats over position, so it still goes as a cosine. The only difference is instead of period, now we have wavelength. So to write down this variation, we know we want the dependence as a function of position. So what is the height as we go down the line? We've got the same maximum amplitude A. It's still sinusoidal, so we still use cosine. When we talked about the time variation, we said cosine 2 pi over the period times t. Here we're talking about position. So instead of 2 pi over period, we get 2 pi over wavelength times x. So there's the description of a wave that repeats every wavelength lambda. When we had 2 pi over the period, we defined our angular frequency omega. We're going to do a similar thing here with 2 pi over lambda. We're going to give that a symbol of k. So we define k. That's called the wave number. The wave number k is given as 2 pi divided by the wavelength. So the units of our wave number is radians per meter, or just meters to the minus 1. Just like omega is radians per second or seconds to the minus 1. Two things just to be aware of here. In our last set of slides, k was the spring constant, now k is the wave number. We use k for a lot of things in physics, so make sure you know which k is which when you're doing your tests and your assignments. It's a small thing, but these small things add up, especially in a high stress situation. The next thing is sort of trying to understand what k means. So for frequency, it's the number of oscillations per second. Angular frequency omega, 2 pi over the period. It's the number of radians per second. It's like a measure of how many, the number of cycles per second. For your wave number k, it's more like the number of cycles per meter. Okay, so those things all go together. Okay, still good? Excellent. So we got a lot of the characteristics done. Let's come back to the wave speed next. So we'd like to figure out what is our wave speed v. And as a reminder, that disturbance travels down the line. Wave speed has a symbol of v. While real waves that you would study, for example, if you did some oceanography classes or some oceanography research, these waves would certainly have changing velocities. It would change over time depending on the weather and the outside environments. We're going to start very simple. We're going to talk about waves with a constant wave speed because it would be very complicated if it started to change. So if we wanted to calculate a wave speed, we know that our speed would be distance divided by time. So if you had a wave that traveled down a 100-meter long string in 10 seconds, the wave speed would be 100 divided by 10, or 10 meters per second. So if you have any distance and the time that goes with it, you could calculate the speed. You could also narrow yourself to ask what is the distance for one cycle and what is the time for one cycle. If you talked about one cycle, your distance would be lambda, the wavelength, and your time would be the period t. So that's also legitimate. You could measure only one cycle. You might remember that 1 over period is your frequency. So V is lambda over the period t, or F times the wavelength, lambda. And then one other thing we could remember is our new definition. So we know that omega is 2 pi times F. And we know that K is 2 pi over lambda. So we could reduce this equation to omega over K. So there are two ways to calculate the wave speed. You can do F times lambda or omega over K. So something I tend to joke in Physics 1020 or 1050, even though I don't find it a joke, I mean it with my whole heart. Something you should remember about physics in 20 years, you're at a party, somebody says physics, the thing you should remember is F equals ma. So Newton's second law is like the most important law in physics. I would say this is the second most. So after you remember F equals ma, you should remember V equals F lambda, because our entire world around us is all about waves, and this describes the motion of waves. So this one is a pretty important equation, and I wouldn't tend to give you this one on a test because I would expect you to remember this equation because it is really important. Okay, let's do an example that uses wave speed, and then we'll get back to our dependence. So the speed of sound in air at 20 degrees is 344 meters per second. So we're talking about a sound wave, and it's moving as a longitudinal wave through the air. What is the wavelength? So we'd like to find lambda of a sound wave which has a frequency of 784 hertz. So we know V equals F times lambda. That tells us that lambda is equal to V divided by F, 344, divided by 784. To get 0.439 meters. That's a pretty straightforward example. We will get to some harder stuff real soon. The next part of this question, so that was what is the wavelength. The next part is how many milliseconds does each vibration take? So the only way I could think of to make this harder was to give a different unit. Instead of seconds, I asked for milliseconds. And instead of straight up saying find the period, I decided to use the definition of a period. So what is the time for each vibration or time for each oscillation? This question says find the period. To do that, we remember that the period is 1 divided by the frequency. So 1 over 784 hertz. Do that in the calculator, we get 1.28 times 10 to the minus 3 seconds. The question didn't ask for an answer in seconds, it asked for milliseconds. So we recognize that a millisecond is 10 to the minus 3 seconds. So this is a millisecond. So we get 1.28 milliseconds. Okay. That's about as hard as that question could possibly be. And then part B is also pretty straightforward. What is the wavelength if our sound wave is 1 octave higher or twice the frequency? So if we double the frequency, what do we get for our wavelength? So we're still going to do a calculation for wavelength, which is V divided by the frequency. Our speed doesn't change, 344 meters per second. Our frequency doubles, so now it's 2 times 784 hertz. So we're going to have the wavelength. So if we double the frequency, our wavelength gets cut in half. Okay, good. Okay, so there's our wave speed and our example. So now we're gonna come back around to thinking about our time dependence, our position dependence, and how do we put it together for a full description. If you printed off the notes or you got the PDF slide, I goofed in typing those equations, which is what I get for doing things tired. I got my X's and T's all mixed up. These equations, the way they are right here, these are correct. So if you have the notes in front of you, please correct those equations so that they look okay. So for the one on the left, we've got our history graph. This talks about the time variation of one of those green dots going up and down. So here's our time variation. For the other one, that's our snapshot. That's where we hit pause. That's the wave along the entire string. That tells us what is the height as a function of position along the line. So if we look at these two equations, we can anticipate that when we put them together to get the expression as a function of position and time, some things we should get in our answer is an amplitude A. So no matter what position and what time it is, it should never go higher than the amplitude. It's a sinusoidal wave, so we expect our answer to have a cosine in it. And if you argue that I could use sine, I would agree, yes, sine or cosine, they're kind of interchangeable depending on the phase constant. We're gonna stick with cosine because your book uses cosine. It changes with respect to time, so we should see something about the frequency or the period in there. So omega, which is 2 pi f, or 2 pi over t, that should show up. It changes over space, so k, which is 2 pi over lambda, that should show up. And whatever the starting point is, that should show up as well. We should also get the phase constant. So this is what we're looking for in our answer. And as we get to this answer, we're also going to be using v equals f lambda or omega over k. So we're going to have to use that to get to our answer. The part where we build our answer, I don't really want to break it up over 2 classes. So if it's okay with everybody, we'll just quit a minute or two earlier and we'll start fresh with this on Monday and we'll get that equation right at the beginning next time.